the refrigeration effect to be produced by this present refrigerator is, I need to use water at 15 degrees Celsius and decrease its temperature to 0 degrees Celsius to convert it into ice. At the same 0 degrees Celsius, I need to remove latent heat of the ice. Hence, I can solidify it and I can get solid ice at 0 degrees Celsius. Here we have the mass of ice, let it as m suffix ice, and its latent heat is 335, and again mass of ice Cp for the ice, then again from 15 degrees Celsius to 0 degrees Celsius, reducing it. So how much time it is taking? It is taking for a duration of 24 hours, 24 into 3600 seconds we have converted, and this is the simplified formula, that is mass of Cp for ice is 4.2 kilojoule per kg Kelvin has been assumed. This is 15, we have kept it as it is. Mass of ice we have taken it common, and finally we formed an expression for total refrigeration effect. So we will use this in the further steps. Mass of we know that mass of refrigerant circulated in the plant is given by the formula mass flow rate of refrigerant is equal to total refrigeration effect divided by refrigeration effect per kg, that is TRE divided by RE per kg. In this formula I will substitute the expression of total refrigeration effect that we have found, and we know the refrigeration effect per kg in the denominator. I will substitute, and again he has given mass flow rate of refrigerant, that is 6.5 kg per minute. 6.5 kg, if I divide it by 60, it will be kg per second. So then converting all the data for SI units, I will write in the next step. So this is total refrigeration effect that we have calculated in the previous step, and again we have mass flow rate of refrigerant as 6.24 kg per minute and divided by 60. Finally, if I operate the calculator, I will be able to get the mass flow rate of the mass of ice produced as 8106 kg. Coming to the next important variety of vapor compression refrigeration cycle, most of the times the problems appears on this cycle only, that is vapor compression refrigeration cycle with undercooling. What is undercooling? Or the another name for undercooling is subcooling of refrigerant. So what is undercooling of refrigerant or subcooling of refrigerant, we will understand in this slide. So here first, as usual, I have compressor, condenser, then again evaporator. After condenser, we are cooling the refrigerant below its saturation temperature, Here how to cool that? I am the outlet of the condenser, saturated liquid refrigerant comes out, then it enters a heat exchanger. So wherein we are supplying cold water into that and hot water is coming out of that heat exchanger by absorbing heat energy from the refrigerant which is coming out of the condenser, thereby decreasing its temperature below the saturation temperature. Means it enhances, refrigerant enhances its capacity to absorb more heat energy in the evaporator. So whenever it enters the evaporator. So hence here we can observe from the temperature entropy diagram, we have temperature entropy diagram. This is saturated liquid line, this is saturated vapor line. After that assume that at the inlet of the compressor, that is wet, we have indicated it on the, then at the outlet of after compression, assume that it is superheated. So 2 to 2 dash it gets desuperheated, 2 dash to 3 gets condensed. After 3 to 3 dash it is coming out as a 3 dash out of heat exchanger, wherein it is cooled. Now here this is the saturation temperature, we are cooling it in the heat exchanger from 3 to 3 dash, that is 3 to T3 to T3 dash, it is cooled in the undercooler device, that is heat exchanger. This process is called as undercooling. Why we are decreasing temperature? If we decrease the temperature, again refrigerant enhances its capacity to absorb more heat energy from the evaporator. So therefore 3 to 3 dash it decreases, but it is in saturated liquid condition only. From 3 dash it enters the throttle wall, so where it undergoes expansion, entropy increases, temperature decreases. This is 3 to 4 throttling process. From 4 it enters the evaporator, so 4 to 1 again it enters the evaporator, wherein it absorbs heat energy from the refrigerated space. Then it comes out at state 1. Then thus the cycle continues. This is called as Vapour power cycle with undercooling. Just observe in the schematic diagram, this is the undercooler. Now the same process can be represented on a pH diagram. This is pressure, this is enthalpy. Here at the inlet of the compressor state 1, outlet of the compressor state 2, 2 to 2 dash it is superheating, 2 dash to 3 it is condensation, 3 to 3 dash, just observe here, 3 to 3 dash, 3 to 3 dash, this is state 3 here, that is condenser outlet, saturated liquid it is. Then 3 to 3 dash it is undergoing subcooling or undercooling process inside the undercooler or heat exchanger, you can say. So the 3 to 3 dash it again reduces its enthalpy, that is change in enthalpy. Enthalpy at state 3 is HF3, enthalpy at state 3 dash is HF3 dash. If I subtract HF3 from HF3 dash, I will be able to get change in enthalpy, that is decrease in enthalpy during undercooling process, delta H. So delta H will be what? It will be equal to Cp into T3 minus T3 dash. So this step we will be using while solving the problems. Please remember this. Now here 3 to 3 dash subcooling or undercooling. Now 3 dash is in subcooled region on the vapor dome. 3 dash to 4 it is isenthalpic process, that is throttling process. 4 to 1 again evaporation. Then we can finally write HF3 dash. HF3 dash is equal to HF3 plus delta H. So this is the equation that we have written. Please remember all these points and we will solve a problem. What all this is very important concept for solving the numericals. Just please remember, this is the device used for undercooling is undercooler, wherein we are supplying cold water and it absorbs heat energy from the refrigerant which is flowing inside the tubes, and the water goes out, but the refrigerant gets cooled, subcooled. See here it is entering the subcooled region from 3 to 3 dash on the pH on the vapor dome, you can say. Now let us solve very important problem on this undercooling process. Here let me read the problem statement. A vapor compression refrigerator using Freon 12 as a refrigerant has its temperatures minus 10 degrees Celsius as evaporator temperature, 30 degrees Celsius as condenser temperature. Now the vapor enters the compressor dry, means at the inlet of the compressor the vapor is in dry saturated condition. Then it is undercooled by 5 degrees Celsius in the condenser, means inside the condenser you can fix a undercooler, or at the outlet of the condenser also you can fix a undercooler, but he says inside the condenser only it is undercooled by 5 degrees Celsius. Okay. For the capacity of 15 TOR, that is 15 tons of refrigeration, find first one we are supposed to find out COP, then mass flow rate of Freon, so at what rate it is flowing inside, then power required to operate this refrigerator. Then again he has given specific heat value for the vapor state of this refrigerant as 0.56 kilojoule per kg Kelvin and Cp for liquid as 1.003 kilojoule per kg Kelvin. Now this is a V2 problem. It was appeared for 10 marks, okay, in a V2 question paper. Now very important variety it is. As we have understood the how to plot the temperature entropy diagram as well as pH diagram for a VCR cycle with undercooling. At the inlet of the compressor, that is state 1 is dry saturated vapor, so therefore it is marked on saturated vapor line. Outlet it is superheated, so 2 to 2 dash, then 2 dash to 3 condensation, 3 to 3 dash it is getting condensed. Now condenser temperature is 30 degree Celsius. This is condenser temperature 30 degree Celsius. What is the degree of undercooling? That is, it is undercooled by 5 degree Celsius. That is, its temperature is decreased by 5 degree Celsius. Now here we have 30 degree Celsius, it is to be undercooled by 5 degree Celsius. 30 minus 5 is 25 degree Celsius, means it is undercooled till 25 degree Celsius. That is, T3 dash is 25 degree Celsius. From T3 dash it undergoes isenthalpic expansion process, 3 dash to 4, then 4 to 1, again it goes. Now here we have pH diagram 1 to 2, 2 to 2 dash, that is superheating, then 2 dash to 3 condensation, 3 to 3 dash, this is subcooling or undercooling process, 3 to 4 3 dash to 4 is isenthalpic process, that is HF3 dash is equal to H4 or H3 dash is equal to H4 simply. Then as usual this is the pH diagram for the present problem. After understanding this, we can note down the properties for the Freon tool from the Freon tool from the data handbook at given temperatures. The properties of a Freon tool are mentioned here from the data handbook. At temperature minus 10 degree Celsius, I have HF, HG, SF, SG values, that is, these are the values from the table. Then at 30 degree Celsius, I have HF, HG value, SF, SG values. Now we are supposed to calculate the unknown parameters that have been asked for solving this numerical. The first one is COP has asked. COP, we know that it is nothing but H1 minus H4 divided by H2 minus H1. This is the refrigeration effect divided by compressor work input. Now where we need to calculate all these enthalpy values H1, H2, then H4 for calculation of COP. Out of that, first one is H1. H1 is here the state 1 is we have marked in the problem statement. In the problem statement, state 1 is at the inlet of the compressor, it is marked on the saturated vapor line. So at state 1 we can apply the formula HF plus HFG directly. So therefore we can we have used this formula, or even you can write HG directly, because HF plus HFG is HG. So HG at state 1, that is at state 1, what is the temperature? Temperature is minus 10 degree Celsius, that is evaporator temperature. So at minus 10 degree Celsius, from this value HF value is HG value is 183.058. So this is Hg value at minus 10 degree Celsius. Thus we determine the value of H1. Then H2, that is enthalpy at state 2, we need to determine enthalpy at state 2. State 2 is superheated vapor in this problem, that can be confirmed from the TS diagram that we have drawn. Then H2 is equal to Hg 2 dash, that is Hg at 2 dash, wherein 2 dash is at 30 degree Celsius. At 30 degree Celsius, Hg value is 199. We will substitute the values later, sorry. And Cp for vapor we need to consider here, because After 2 dash, the condition of the refrigerant is vapor. I can't use Cp liquid here. So, this is Cp vapor, and again change in temperature is from T2 to T2 dash. That is how we need to write the formula, that is T2 is superheat temperature minus saturation temperature is T2 dash. So, now we will substitute the values, that is Hg2 dash, Hg2 at 30 degree Celsius, Hg at 30 degree Celsius is 199.475, then Cpv he has given himself in the given data, that is 0.56, then T2 is unknown, superheat temperature is unknown, we are able to find out now, then T2 dash is 30 degree Celsius plus 273, in Kelvin we wrote this. Then for T2, but T2 is unknown in that equation. I want enthalpy H2, but T2 is unknown in that. What is superheat temperature we do not know. For calculation of T2, as usual we know, we consider the process 1 to 2, that is isentropic process. So, wherein S1 is equal to S2 for 1 to 2 process. S1 is what? S1 is, that is entropy at state 1. Entropy at state 1 is Sg1. Sg1 is, that is at minus 10 degree Celsius. Then is equal to, what is S2? Entropy at state 2 is, that is superheat state it is Sg2, that is Sg2 plus Cp ln of T2 dash upon T2 upon T2 dash, T2 upon T2 dash in this problem. That is T2 is superheat temperature, T2 dash is saturation temperature. So, this is the formula from the basic thermodynamics, Sg2 dash plus Cp ln of T2 dash, T2 upon T2 dash. If I apply this formula, I will be able to calculate the value of T2, that is superheat temperature, wherein Sg at minus 10 degree Celsius, Sg at minus 10 degree Celsius we have this value, we have substituted here. Then again Sg at 30 degree Celsius, Sg at 30 degree Celsius we have this value. Then Cpv he has given, Cp for the vapor 0.56, then ln of T2 upon T saturation temperature between 2 and 2 dash is, saturation temperature is 30 degree Celsius, 30 plus 273 we have indicated. So, using mathematics I am able to calculate temperature as 312 Kelvin. Then H2, now I am able to calculate H2 now. So, I will substitute T2 here, then enthalpy at state 2 is calculated. Then enthalpy at state 3, enthalpy at state 3 can be calculated by H4, H4 is equal to H3 dash, H4 is equal to H3 dash, again H3 dash is HF3 dash, HF3, that is same pressure is constant here, that is HF at same pressure, that is or same temperature you can say 30 degree Celsius, HF3 at 30 degree Celsius, then minus this enthalpy minus the change in enthalpy during subcooling process. So, this formula we know already, H3 dash is equal to, from pH diagram, HF3 dash is equal to HF4. I want HF4, but we have the value, that is HF at minus 30 degree Celsius. So, this is HF3 plus the change in enthalpy, that is delta H is equal to HF3 dash. Same formula we have written here, that is H3 dash is equal to HF3 dash is equal to H4 is equal to HF at 30 degree Celsius minus the change in enthalpy, that is Cp but what is the state here? Between 3 and 3 dash, the condition of refrigerant is liquid. So, therefore, Cp for liquid I have to use here. Then 3 to 3 dash, there is a decrease in temperature. So, hence H4 I am able to calculate. This is a very important step for undercooling process. Now, here I am able to calculate H4 using mathematics, that is H4 as 59.524 kilojoule per kg. Once I calculated the enthalpy values, all these enthalpy values, so I am able to calculate COP now. So, this is the COP. Mass flow rate of freon we are supposed to calculate, that is mass flow rate of refrigerant is equal to refrigeration capacity, that is refrigerator capacity or total refrigeration effect, that is 15 TOR he has given, divided by refrigeration effect per kg. So, then we know that 1 TOR equal to 3.5 kilojoule per second. Then we substitute the refrigeration effect per kg as H1 minus H4. Then we are able to calculate mass flow rate of refrigerant as 0.4269 kg per second, or finally in kg per minute 25.61 kg per minute. Then power input to the compressor, we know this formula, mass flow rate of refrigerant into H2 minus H1. Mass flow rate of refrigerant in kg per second value is there with us. Then H2 and H1 are already calculated. So, operate the calculator, I am able to calculate input power as 9.81 kilowatt. Then theoretical cycle, one more variety, that is Vapour power cycle with superheated vapor before compression. Just theory we will discuss. So, here we know after evaporator, heat absorption is in 2 stages in this, 4 to 1 dash, that is till it becomes dry. Then still heat absorption is happening for the refrigerant from 1 dash to 1, that is at the inlet of the compressor state 1, it is completely superheated vapor. Then we can represent superheating process on pH diagram between 1 dash and 1 dash is marked on dry saturated vapor line, then 1 is in superheated zone. So, 1 to 2 again it is superheated. This is the superheating process we can represent on pH chart. Now, in this cycle the evaporation starts at 0.4 and continues till 1 dash, that just now we have discussed, and it is dry saturated. Then the dry saturated vapor is superheated by absorbing heat energy from the refrigerated space, then enters the compressor at 0.1. Now, in this cycle the heat is absorbed in 2 stages, first from 4 to 1 dash and second from 1 dash to 1, point to be noted. Then COP for the this present cycle is again remains same, H1 minus HF3 divided by H2 minus H1. Now, we will solve a simple numerical on this. The change in the problem statement is vapor is superheated by 5 degrees Celsius before it enters the compressor. Now, these are the properties of refrigerant mentioned in the problem statement. Just I request you to pause this video and note down the problem statement for your understanding. Now, here we have the saturation temperature in Kelvin, then superheat temperature, again here superheating 259 is a evaporator temperature, superheating 259 plus 5 degrees Celsius, that is 264. This is 1 dash to 1 is superheating process he has mentioned. This is how the superheating is mentioned on the pH diagram for marking. This is H1 dash, this is H1, again H2 is there. Now, this is the given data with the notations with the notations that that is shown on this screen, corresponding notations, and this is the enthalpy at point 1, H1 dash is equal to Cp into T1 minus T1 dash. Then H1 dash itself is HF1 plus HFG1 or HG1 you can mention. Then Cp into, these are the given data, and degree of superheat is 5 degrees Celsius, he has mentioned here, that is 5. Then again enthalpy at point 2 we are supposed to calculate, that is H2 dash plus Cp into T2 minus T2 dash, which is H2 dash is again HF2 plus HFG2 or HG2, you can note down the value from the data that we have noted down from the table given data, and we substituted the values and we are able to calculate enthalpy at state 2. Coefficient of performance of the plant, substitute the known values and get the COP value. Thank you. So, we understood different types of vapor power cycles in this video. For any clarifications, please feel free to contact me. And again, the important cycle to be remembered in this video is the VCR cycle with undercooling, and we must be able to plot pH diagram and TS diagram for undercooling process, VCR cycle with undercooling process, and we must be able to solve numerical on the problem. That is very important. So, that is a request from my side, and thank you for watching.